So the first part kind of proof we're going to be learning is a thing known as direct proof. And it literally just means what it is. You take an assumptive case and then just mess around until you get the result. However, a common thing to note with this is how you represent odd and even numbers. So, I'm just going to do that real quick before we dive into this proof. So all odd numbers are one more than an even number, and even numbers are multiples of 2. So an even number can be represented as 2 times some number k, where k we generally have is greater than or equal to 0. We're only considering positive integers here. Now, because an odd number is sort of midway between two even numbers, the next even number is 2 times k plus 1, which is 2k plus 2. Therefore, an odd number has to be between 2k and 2k plus 2, which is 2k plus 1, again with k greater than or equal to 0. So how do we tackle this question here? Prove that for all odd integers of p greater than or equal to 3, p squared minus 1 is a multiple of 8. So when it just says prove that, you can use any method you want. You can use induction, which is going to be a future technique we're going to know. But for here, we're going to do a direct proof step. So how do I do that? Well, at the beginning, you say let p equal 2k plus 1 because it's odd, again stating that k is greater than or equal to 0. Then you just say let p squared minus 1 equal 8 times some multiple, which I tend to call a, where again a is greater than or equal to 0. So we know p is 2k plus 1. So I'm going to sub it back into here. So we get a 2k plus 1 here is equal to 8a. Expanding this, we get 4k squared plus 4k plus 1 minus 1 is 8 times a. So we end up getting 4k squared plus k, then the plus 1 and minus 1 cancel, or 4k, sorry, equals 8a. Now, you might be thinking that there's something a bit odd here, the fact that there's multiples of 4, but then we get an 8a hanging about. Now, there's a couple ways you can deal with this. The first way is we go back to this odd even stuff. So let's do method 1 for the odd even. If we do indeed take out a 4, and we're left with k squared plus k is 8a, we now have to show that k squared plus k is therefore always even. So if this is even, it is a multiple of 2. And 4 times multiple of 2 will always yield a multiple of 8. So let's test k is even. So that implies that k is 2 times some other number, say x, because you're going to use that. We'll end up getting 2x squared plus 2x, which simplifies down to 4x squared plus 2x. And then if we take a 2 out the front, we get 2 times a number, so 2 times number, which is even. So if k is even, then this must be true. But what happens if k is odd? Well, k is going to be 2x plus 1. Therefore, we'll have 2x plus 1 squared plus another 2x plus 1. Simplifying this, we get 4x squared plus 4x plus 1 plus 2x plus 1, which ends up being 4x squared plus 6x plus 2, which again we can simplify a 2 out of. Again, that is even. So if we've proved that, so proved for all k greater than or equal to 0, k squared plus k is even. Therefore, 4 times 2 lots of an even number, or one even number we'll call b, is always equivalent to 8a for some a and b. Okay, so that's the first method. The second method, it requires a slightly more nuanced factorization. So that's the first one. The second one, if we go back to 4k squared plus 4k is 8 times some number. If we instead take out a k, we'll have 4 times k. That's from this. And then if we take a 4 out of the whole thing, kind of this bit quick. So if we actually take a 4k out, we get k plus 1, which is 8a. Now, if you pay attention to this, we have an odd number times an even number, technically, or, in other words, this is a product of two consecutive integers, which is an odd times an even. So it's handy enough to know that if you have an odd times an even, so we'll say 7 times 8 as just an example, it's 56. If we do 6 times 7, it gets 42. Even something which is 11 times 12 is 132. We're always going to end up with an even number. So this is always even. You can prove this yourself using direct proof if you want to. But we can show that it's going to be 4 times, again, another even number. So, again, therefore true, sum A and B. And that is a nice example of direct proof.